Lab 6, Magnetic Molasses. So for a quick introduction into this lab, the goals are to observe Faraday's law by measuring how the motion of a falling magnet is affected as it travels through a conducting tube. Then we're going to find out how this induced electric current and magnetic fields slow the movement of the magnet. And a preview of the findings, magnets with a larger magnetic dipole moment induce stronger currents in the tube, and stronger currents equals a larger opposing magnetic field, resulting in a more noticeable change in the magnetic's falling behavior. So some key concepts to go through is one, Biot-Savart law, which basically explains how those induced currents create a magnetic field that opposes the motion of the magnet. And then we have Newton's second law, which governs the magnet's motion. And then we have Faraday's law of induction, which describes how changing magnetic flux produces electric currents. Now, moving into the experimental procedure, we have our system and surroundings, our system being the magnet and the foil, and the surroundings being gravity. The setup is just dropping a magnet through an aluminum foil tube while recording, monitor the speeds of the magnet and then monitor the speeds of the magnet falling through this tube. And some possible sources of errors while looking at this procedure would be inconsistencies in timing measurement and then lack of precision in calculations. Now the experimental data is length of the tube is 0.05 meters, width of the foil is 0.2 meters, magnet mass is 0.37 kilograms, the radius is 0.18 meters, and then the magnetic dipole moment found was 1.33 ammeters squared, and the average drop time was 2.3 seconds. And here's the computational model with the glow script code and the experimental model. Now, from the experimental model, we can see that the simulation produced a fall time that mirrored the fall time in the actual experiment, and that the induced current from the foil was counterclockwise, and that did not depend on the direction that the magnet was dropped from. Now, when we go into our what-if questions, we can ask, what if the resistivity of the conductor was reduced as close as possible to zero? And how would that change the dynamics of the falling magnet? And so it would change because in order to have the magnet fall at the same amount of time, there needs to be an additional magnetic interaction between the aluminum and the magnet. And we go to our next what-if question, which is, what if holes or slots were cut into the tube? How would this affect the ring currents in the model? We can know that the holes would reduce the material in the tube, which would reduce the induced magnetic fields because of the interruptions in the current. Thank you.